So what is a register? Register memory it's nothing but smallest and fastest memory in a computer. It is not a part of the main memory, and it is located in the CPU in the form of register, which was the smallest data holding element. So as we have the idea of memory till now, that what are the memories and why we use those memories. So the main reason why we are using this memory is also the same, to storing the data as well as to cope up with the speed of the CPU, right? Any register temporarily holds frequently used data, instructions, and memory addresses that are used by the CPU. So as this register is a memory which is inside the CPU, and it will help the CPU to store the frequently used data, instructions, and memory addresses. And it is very much essential for a CPU to get all these data. They hold instructions that are currently processed by the CPU. So yeah, that is currently processed by the CPU means if a CPU has just processed the data, so that data also has to be stored in any of the register. All data is required to pass through register before it can be processed. So all data, whenever we want to give it to the CPU, it has to be there in the register. They are used by CPU to process the data entirely by the user. Register hold a small amount of data, around 32 to 64 bit. The speed of CPU depend upon the number of size of the bits of the register that are built on the CPU. So whenever this we find out that the size of the register is more than that amount, so definitely that CPU will become more faster. Register can be of different type based on their uses. Some of the widely used register include accumulator, that is called AC, data register, that is called DR, address register, it is called AR, program counter, that is called PC, IO address register, and more. Now after that, there are different types of register. What is the first register? Is the data register, where we store the data by which we do the operations. Program counter, it holds the next address of the instruction, next instruction address, and it is there in the memory, so that it will store the memory location of it. Instruction register, here it will hold the instruction which it is going to fetch from the main memory, so that instruction has to be there in the instruction register. Then we have accumulator register, in which whenever the CPU will process anything, that process data will be stored in the accumulator register, AC. Then we have the address register. It will hold the address of the instruction or the data. Then we have IO address register. This is attached with the any IO devices, input output devices, and it will hold the address of that particular device. And then there is a buffer register. So whenever the data will be sent to that particular and it is required by the IO, so that is stored in this buffer register. Okay. So yesterday I have given you one glimpse or one example of how these memory, this registers will work actually. So I'll explain that example again today so that you can understand it very deeply. So all memory that we are talking about here, so we are talking about two type of memory. One is the main memory, another is a register. Register is, as we know that it is inside the CPU. Okay, so let's talk about first the main memory. So we have a main memory exists with us, and this main memory is of 4096 into 16. This is the size of the main memory. So main memory is nothing but your RAM. Okay. And what is the 16? 16 is nothing but the word size. So operating system deal with the word. And as we have discussed in last few classes, that there is a smallest what? The smallest structure is nothing but the bit. Then 8-bit will become byte, and then we are talking about word. The word is here of 2 byte. You can see, because it is a 16-bit word, it means it is of so it is of 2 bytes. 1 byte is 8-bit, right? So and this word is used by the operating system, and how the operating system is based on that, this word will be increase or decrease. Okay, now let's draw the main memory that we have. Let's say we have the main memory exists, and in this main memory there are 1096 locations where in each block 16 word can be accommodated. So we'll put like that so that you can understand that there are a bunch of blocks, and in each block we have 16-bit of data exist. And how we can differentiate between the addresses? So we can differentiate between the addresses with the help of 4096. So 4096 we can represent with the help of 2 to the power of 12. It means that each and every memory location of the block could be represented with 12 bits. So let's say for this we have 000 up to 00, means this is of 12 zeros. This is one memory location. Then we have, this is 01. This is the first, this is the first, this is the second memory location. This is the third memory location. And this is the fourth memory location. And in that way, this addressing will go on. Okay. This is about addressing. And here we have word of 16 bits. So here the size of this will be 16 bits. This is the size of this one block. Now let's talk about different type of registers that we have. So the first register that we have is address register, that is also called AR. What is there inside the address register? Inside the address register, this address value will be there of any of the instruction that is there in the block. Okay, and each block we have some sort of instructions or the data, right? So for instruction or the data, this address register will hold the address of that particular memory location where it will get, the CPU will get the data or the instruction. Because in the von Neumann architecture, we know that instruction and data should be resided inside the main memory. So it is inside the main memory. So what should be the size of this particular address register? Because it will hold the address of this particular memory. So it will be from 0 to 11, it means it is of 12 bits, because with the help of 12 bits, we can represent one address here, right? So it is of 12 bits. Next, we have data register, DR. In the data register, we'll store the data which we are fetching from any of these blocks. So definitely, if we are fetching the data, it should be of 16 bits, because we are fetching from the blocks. So the maximum size will be of 16 bits, 0 to 15. It will be of 16 bits. Next register where we have is program counter, that is also called PC. What is that program counter? Program counter will hold the next instruction address. Let's say here we have fetched the instruction I1. Instruction I1 we have fetched previously because the address was there. After that, what will be the instruction after that? So there is an instruction I2. And what is the address of this instruction I2? This is the address of the instruction I2. So this address will be held by the program counter. So because it is holding the address, the size will be of 12 bit. This is your program counter. Then we have another register which is called accumulator, which is, in short, we say AC, accumulator. This is called accumulator register. What is the size? What it will do? Accumulator register will hold the result generated by the CPU. If CPU will execute any instruction, that result will be stored in accumulator register. So definitely it will store some sort of data, and data size is of 16 bit. So it will be, the addressing will be 0 to 15. It means it should be of 16 bits. Now, after that, we are talking about another special type of register, which is called instruction register. This is called IR, instruction register. What is this instruction register? Inside the instruction register, we should have the instruction. How it will be divided? It will be divided into 3 parts. So the first part is your which type of addressing we are using. So it is talking about addressing. To fetching the instruction from the memory, what type of addressing we are using. The second part is of the operand. What is the operand? It is of, so it is of 1 bit. Operand is of 3 bits, and the rest of this is the address of the data. So it is nothing but this. Okay, this is not the operand. This is actually the opcode. Opcode means your operation code. Okay, so I'll write it here. Opcode, some sort of operation. Then we have operand here, or the variable or the data. So I'll write data, or we can say it is a operand. This operand will be here, and not operand actually, the address of the operand will be here. It is of 12 bits. So in the instruction register, the total size will be from 0 to 15. It is of 16 bits. And this opcode is of 3 bit. In the opcode, what will happen? We have, in the opcode, we have some sort of operation, like let's say if ALU have the instruction called multiplication. So we have a multiplication operation here, or it will want to do some sort of addition. It should have an addition operation, subtraction operation, or division operation, or mod operation. Whatever operation it is doing, we can represent it with the help of 3 bits. So actually these are stored into the memory. So it has again 3 parts. You can see this is your either 0 or 1. So this particular part will be either 0 or 1. 0 will be your direct addressing and 1 will be your indirect addressing. So what is, if we are making a direct addressing, means if we are making it 0, let's say the opcode is addition and there is some memory location which is written. Let's say 450 is your memory location of the data. So once we'll go here, we'll read 0. In that we'll find it out that it is a direct address of the data. So let's say this is your 450 location. Let's assume that this is your 450 location. You convert it into a decimal. Okay. So yeah. So the instruction will be read here. It will be stored in the instruction register, and then it will go to the address of it. That address will be fetched here, and it will go to the address of it. So here we'll find out the data. Let's say the data is A, some sort of variable, and the value is there with the A. What happened in the indirect addressing? Let's say we have an indirect addressing, and this in indirect addressing will be represented with 1. Okay, and let's say we have an operation of multiplication, and we have the address of, let's say, 550. Let's assume that this is your 550 location. You can convert it into some sort of binary addresses. Now, when it will go from here to here to get the data, it knows that here also will not get the data. Here it will get the address of it. So it will go to the address of it. Let's say the address is 120, and here it will find out, let's say, 120 location. So now from here, the control will go to that particular place, and here it will get some sort of data. So this is how your instruction register work, and we have the instruction on it. Okay. In the detail, you will learn about the addressing. You will learn about learn in computer organization and computer architecture. Now after that, we have some register for the IO devices. Okay, that is called IO register. One register is your IO address register, and another will be your IO buffer register. Okay, so generally it is depend upon again the architecture of the CPU. It is of generally it is of 8-bit, because when we get the instruction from the keyboard and all, we'll use to take one character. So one character we can represent with 8-bit. So this is how your whole register is there, and this is how it is working. Okay, storage hierarchies. So we know what is this hierarchy is. This hierarchy is based on the 3 factors: cost, speed, and volatility. Volatility means how volatile it is. Volatile means if a memory, we say it is a volatile, it means that memory can store the data for a temporary period of time. What is the temporary period? Up to its power. So whenever we remove the power from the memory, it cannot hold the data. And non-volatile means those memories, if we give the power or without the power, it can able to hold the data. So you can see that magnetic tape we have, which has the lowest cost and the lowest speed, and it is non-volatile. That is your magnetic tapes like cassettes and all, right? Then we have optical disk, that is your CD ROM, CD CD and the DVD and the Blu-ray disc. So all those comes under optical disk. Then we have hard disk. Hard disk is your magnetic disk. We talked about it. So you can see that, as well as the solid state disk. Solid state disk is made from the flash memory or the flash drives memory, and we have the microcontroller over it, and we have the cache. It is faster than the hard drive, and it is the cost is also more than the hard drive, and it is also a non-volatile memory. So from here to here you can see all are non-volatile. Okay, now if you'll go from here to here, it's all volatile memory. So we have main memory, which is your RAM, right? Random access memory. So I told you the difference between what is the DRAM and SRAM. So here generally main memory is your DRAM, cache is your SRAM, static RAM. Okay, main memory is your dynamic RAM, but we generally see RAM. So this main memory is there, which has the more storage capacity, but the cost is less than the cache memory, and the speed is also less than the cache memory. Then we have the cache memory. We have three type of cache: L1, L2, and L3 cache. L1 cache reside inside the CPU. Then we have L2 cache, which is outside the CPU, and then we have L3 cache, which is also outside the CPU. Then we have registers. Registers always reside inside the CPU, and we have seen different type of registers. And you assume that register is the fastest memory among all the memory hierarchies. So this is all about your different memory hierarchy. Okay, quickly we'll go to the von Neumann architecture design or architecture diagram. See, we have two computer architecture. One is called Howard architecture, another is called von Neumann architecture. So in today's computer, or in today's computing devices, we use von Neumann architecture. Von Neumann says that the data and the program, or the data or the instruction, should reside inside the memory. And whenever CPU want to execute the data or the program should be there in the main memory. So that is the architecture given by John von Neumann. He is a scientist and given the name von Neumann architecture. Here the input devices are there which are connected with the CPU, and output devices are there. The main memory is also connected with the CPU. Here CPU has three parts. Some CPU has another part which is called cache. The first part is called CU, that is control unit. Second part is called ALU, that is called arithmetic logic unit. In the arithmetic logic unit, actually your processing takes place. So here we have the different type of circuitry is there which will do the execution for you. So we give the data from the register, and register we have address register, data register, then program counter, accumulator, and we have instruction register, we have IO buffer register. So all type of registers are there. Control unit will make the decisions that what data to fetch from the register and put into the arithmetic logic unit, and from the arithmetic logic unit what result has been generated, and the result has been stored into the accumulator. So control unit will control the operation in the central processing unit. So this is a brief summary of von Neumann architecture that we are using in today's world. Now we have different computer architectures also. Like generally we have single general purpose processor which look like this. We have only one CPU exists, and register ALU and control unit is there, is the part of CPU. and sometimes we have multiprocessor exists. So in one system we have multiple processors that or multiple processors that may exist, and this is for parallel system, and they are also called tightly coupled system. Why it is called tightly coupled system? Because all the CPU will be interacting with another other CPUs or other processor which are there in the system. So they are tightly known to each other, and they know how to do the execution with the data and the instruction that are given to the processor. What is the advantages of multiprocessor? If we have multiple processors in our system, so definitely the throughput will increase. Economy of scale means economically, yeah, it is costlier, but the result you will get increased reliability, because if one CPU fails or if one CPU halts, so we have some other CPUs or the processor exists that can do the process. We have two type of multiprocessing system. One is called asymmetric, another is called symmetric. In the asymmetric, each processor is assigned a special task like this. So if we have this asymmetric multiprocessing architecture, in which each and every processor will given different program to execute. Symmetric multiprocessing operating system, symmetric multiprocessing system, what will happen in that? Each processor perform all tasks. So each processor will perform, let's say there is a P1, which is one program will be divided, and all processors will given this P1 for the parallel processing. This will increase the throughput. Okay, this architecture actually increase the throughput. This architecture may increase the reliability of it. This is also increase the reliability, because if one CPU fails, so we have some more CPU which can deal with this particular fault. So fault tolerance system we can make if we have multiple processor exist in a system. Symmetric processing, symmetric multiprocessing architecture look like this. So as we have discussed, is one program is given to each and every processing unit, and through the multi-threading, here we'll divide the process into different threads, and threads will be provided to the CPU. Inside the CPU, we know that we have register and the cache, and memory is there. Memory, from memory, the program will be fetched and divided into threads, and parallelly all the CPU will execute it. That is called symmetric multiprocessor architecture. We may have these type of architecture where we have one CPU, but we have different cores available. So right now we see these type of architecture in the laptops and in the desktop, like dual core, 4 core, 8 core CPUs. It look like almost the same, because every processing unit or every core has its own register and its own cache available. Let's talk about clustered system. Okay, so yesterday we have stopped our class here, so we'll deal with this. So let's go to clustered system. What is a clustered system? Like multi-processor system, but multiple system working together. It looked like the multiprocessor system, but here multiple systems working together. Here it is not like only one unit is there, and inside that we have multiple processors. No, it is working as a multiprocessor, but it is not the one system we are talking about. Here we are talking about multiple systems. So if multiple system will be tightly coupled and they are working in a architecture, that particular architecture is called clustered architecture. Okay, and usually we use for in today's scenario where we are talking about reliability and fault tolerance, we use the clustered system we use storage area network architecture into the clustered system. Okay, we have another architecture which is called network attached storage. Okay, and we have a storage area network. So let's take and find it out the difference between storage area network and network attached storage. Okay, and then we'll come here again we'll see what is there in the clustered system. Okay, so the first one that we are going to discuss is called network attached storage. Okay, as the name suggests, it is also called NAS architecture. As the name suggests, we have a storage area, and this particular storage area has different storage devices. Let's say you have multiple hard drive available in the form of RAID, that is called redundant array of independent disks. You might have seen this particular type of concept in database management system, where we have redundant disks are there, and all these redundant disks are there in one system. So you can see this is your storage unit. Okay, you assume that this is your storage unit. Here we have some sort of controller which will give the power to this particular unit. And this particular unit is attached with some sort of access point. So assume that this is your access point, or you can say some sort of router by which this is attached. And with the help of router, many computing devices are attached. Let's say you have your desktop or the laptop which is attached. You might have some sort of what you can say a particular system which is attached, or you may have some sort of server that are attached. So all these devices are attached with the network, and this network is attached with the storage unit, and all these devices can access the storage whenever they want with the help of network. In this particular architecture, it is a good architecture for a personal use or for a small firm, where the fault tolerance will not be a problem. So what happen in fault tolerance? Let's say if this particular system fails some time, so what will happen is nobody can access this particular data. So the data will be cached, nobody can access it. Or if the network will not be here, so nobody can access it, right? Nobody can access the storage area or the storage unit. Now this was the problem, because here we doesn't have the concept of fault tolerant. Fault tolerance means can we make another provision so that that fault can be rectified. So you can say this is not the robust system, means from the failure we cannot come back. Okay, so this was the disadvantage related to network attached storage. Now let's talk about storage area network. that is called SAN, storage area network. So what will happen in the storage area network and what is the architecture of a storage area network? So here we have some sort of databases exist where we have multiple disks available. This is your storage area, and you assume that this is your power unit to this particular storage, right? Now all this storage is attached with some sort of switches. So we have the network devices. So we have some sort of switches. And we have some sort of servers. So this particular part, we have servers, switches, and actually storage. Now here, what is the architecture it has? It will be connected with all these switches, right? And it is also connected with that in the same form. You can see it is just like a mesh network. So what will happen here? These are the servers, right? These are all servers, and these servers can access the storage with the help of the networks, right? And if any of the system, let's say this storage fails, so what will happen is here we have some duplicate data also. So it is not like only one data is stored in one place. Here we have duplicate data which are stored in different places. So actually storage is more important than your switches and the servers, because servers will just serve whatever requests that come to it. Let's say a laptop has or a computing device has requested for one particular data. So it will go to the server will go and find it out where the data is. It will fetch it again, given back to the client, right, in this particular architecture. And what will happen is these data is stored in a duplicate form, in a redundant form. So here in one unit we have the concept of RAID. Here in different units we have the concept of RAID, redundant array of independent disks, where redundant data will be there. Means a copy of the data will be stored. Let's say we have a data A. So the copy of the data A dash will be stored in different storage devices. So if let's say one fails, so we have the copy in another storage device by which it will take the data. Let's say one switch fail, so from other switches it can be connected. If one server fails, so from different server it can be connected. So this architecture will be used in today's cluster computing. Okay, so I think you might understood the difference between network attached storage, that is called NAS, and SAN, which is called a storage area network. So this storage area network, because of the high clustered system, it provides a high availability services which survives failure. So as I told you, any type of failures can be survived by this architecture. Asymmetric cluster, what happened, and symmetric cluster, what happened. In asymmetric cluster, has one machine in host standby mode, in hot standby mode. In symmetric clustering, has multiple node running application monitoring each other. So in asymmetric clustering, what will happen is only one machine will serve, and one machine will have the responsibility to do all the serving thing to the client. But in asymmetric, all the machines should be active, and cumulatively they will do the work and get the data to the client. So that will happen in asymmetric, and each and every unit is running in your cluster architecture. Some cluster are for high performance computing. As I told you, we have in our institute high performance computing which exists, and it will follow storage area network architecture. Applications must be written to use parallelism. Parallelism should be there, means let's assume that I'll show you what do you mean by this parallelism. So to connect with this particular network, it should be a network device, right? Some sort of network device. So what will happen is every request from the client will go through this particular network device, and this network device will give the request to any of the server. Now what happens when we are using asymmetric? So network device will give, let's say, the request to only one server, let's say this server, to serve, and this server alone is responsible for serving the request to that particular client. Now what happens when we are using symmetric system architecture, in which the request will be divided parallelly and the parallelism will be followed and given to different servers. And these servers, let's say the parallelism is, let's say it require let's say 30 something, so 30 unit of data. So what will happen is the network will divide the request to 10, 10 and 10, and all these server will serve. And because it is not the 30 that we are talking about here, we are talking about, let's say 10 units. So it can serve very fast. So 10 unit can be fetched from the database and can be served very fast, and in that way they can be achieve parallelism. As well as if they want, let's say we have 3000 line of codes, and it need the server and the memory so that it will actually execute it as quick as possible. So it will use this particular architecture. Okay, so this 3000 code has been divided into 1000 code. Depend upon that all these 1000 code are independent to each other by applying the parallelism, and these 1k 1k and 1k code has been given to the server. If they need the memory, it will use it, otherwise they will serve and they will give back the result to the client. So that will happen in symmetric architecture. In the asymmetric architecture, only one unit is active, and the parallelism would not be possible in symmetric clustering. Some have distributed lock manager to avoid conflict operation. So in some architecture, we have distributed lock manager, which will look for the conflict operation. Means, let's say if we have so many requests that are coming from different clients, and if they require the same data to be same, they all are working in the same data. So what will happen is there is this distributed lock manager which will look after the conflict request. So if only one shared data will be requested for the manipulation, it is not going to provide it. Okay, so it will look after the data also in a concurrent request or concurrent processing. So multiple processes, if it is processed by these servers or by these control units, so definitely it will look for the processes with the conflict. So if there is no conflict, so it will be bypass it, and it will be served and given back the result.